Assalamualaikum and good day. So today we're going to discuss the last subtopic for Laplace transform, which is called as the Laplace of derivatives. Similarly to the idea that Laplace of integral is used when you want to Laplace something that involves integration. So Laplace of derivatives is used when you want to Laplace something that involves derivatives. For example, if you have something like dy over dt and you want to Laplace transform that, so this is going to be the formula that you wanted to use. Or you come across something that goes like Laplace of, let's say it's got to be, so instead of y, let me use another notation. For example, you come across something that goes x double prime. You know that this is actually d square x over dd square. And you want to Laplace transform this. So this is the formula that you want to use. Okay, and it is actually a very simple formula. So this is actually the simplest out of everything that we have seen before. This is even easier than linearity theorem, but I don't know why it can get quite confusing for students. And actually, when I mark final exam papers on solving differential equation using Laplace, so this is actually like the most mistakes that student did, copying down. Surprisingly, you guys seem to be really bad at copying, seriously. All right, so the Laplace of derivative says that if Laplace of f of t is equal to f of s, then if you want to Laplace the first order derivative, so this is a first order derivative, so the f over dt, so which is the same notation. So these two are actually different notation but the same thing, the f over dt or f double prime. So if you Laplace transform that, the outcome is going to be s f s minus f of 0. And if you Laplace second order derivative, d square f over dd square, or which is the same as f double prime, so the outcome is going to be s square f of s minus f naught minus f prime of 0. So that is actually a general form for this, which looks like this. So this is going to be the general form. You can find this in the book as well. General form meaning that this formula over here, so this applies for any order of derivative. If you have second order, third order, fourth order, fifth order, so this will be the formula. Okay, however, at your level, if you notice, we stick to solving first and second order differential equation. So that is why. So we are only going to focus on these two, Laplace of first derivative and also Laplace of the second derivative. Okay, before that, there are two things that I want you to notice about the formula. So the first thing that I want you to notice about the formula is that, so only the first term is capital, right? So make sure that when we mark the final exam, we were able to differentiate between your capital letter and your small letter. I have a really hard time trying to guess when marking the test, when we do the plus, when we do homogeneous best substitution, whether this is capital, whether this is going to be some smaller case. So make sure we are able to differentiate that. Make a way to differentiate them. All right, so here, I want you to notice the fact that only the first term is going to be in term of capital F. And this one also, only the first term is going to be in term of capital F. The remaining terms at the back is going to be in term of small f. So that is if you're using f as your variables. But you don't have to stick to f. It could be dy over dt or dx over dt. And all you have to do is change the x to be f to be in term of x or y or whatever your variable is. Okay. And then, so the next thing is that... So that is the first thing that I want you to note, to the fact that, so only the first term is going to be capital. So the second thing I want you to note that only the first term is positive. Okay, only the first term is positive. So if you notice right here, so this is positive. So I'm going to put a red pen on this. So this is a positive. This is a positive as well, but the remaining term at the back is going to be negatives. And even if you have a look at the general formula, so only the first term is positive, but other than that, everything is going to be in term of negative. So when you copy this formula, please copy them very, very, very carefully. Remember, only the first term is capital and only the first term is positive. The rest of them are going to be in term of small case, and they are going to be negative. Okay, let me show you an example. Okay, for example, so previously, let me write down the formula first because you're not familiar with that yet. if I have Laplace of first derivative f prime, so the formula is going to be SFS minus f of 0. And please do not worry as well, because you don't have to remember this. So this is given in the appendix section in the exam. So let me show you where's my appendix here. So this is my appendix. So it's going to be right here. So this is the formula, first derivative and also second derivative. Okay, so let's say I'm not using the variable f anymore. So let's say here I'm going to be using, I wanted to find what is going to be the Laplace of dx over dt. So that is actually just Laplace of x prime. So I'm just going to copy this formula term by term. The only thing that I have to do is I have to replace the alphabet. Instead of using variable f now, everything should be in terms of x. So whenever there is capital F, this is going to be replaced by capital of X. And whenever there is F right here, this is now simply going to be small case of X. That's it. So that is a very, very, very simple formula. And let's see the case of second derivative. So according to the formula, Laplace of the second derivative is going to be given by s square f of s minus sf of 0 minus f prime of 0. So that will be the formula. So when I apply this, for example, let's say I want to find what is going to be the Laplace of d square v over dt square. So that is actually equivalent to Laplace of v double prime. Okay, remember, only the first term is capital. So I'm going to end up with s square capital V of s minus s v of 0 minus v prime of 0. And the last term for second order, it's a prime. So v prime of 0. Okay, another thing that I would like to explain to you is that what does the term at the back actually means, the f naught? Why is it not? Why sf naught and f prime of 0? So naught means 0. So f0, f0 and f prime 0. So what does this tree means? So they are actually something that you have seen before. Remember, like we have general solution and particular solution. And when we want to find a particular solution, so we need initial condition. For example, you're going to be given something like this. You're going to be given that y1 is equal 0. So we know that when x is equal 1, y is equal 0. And remember, this is called as initial conditions. And that is the same for this case as well. So this f naught, f prime naught, they are actually initial conditions, and the value will be given in the equation. All you have to do is substitute. So let me put right here. So they are called as initial conditions. Okay, or shorthand will be IC. Don't worry, you will understand this better when I show you the example. So the next thing is that let's have a look at the example. So for the first example, no, this is going to be the only example, in fact, because it's that simple. So I'm going to find the Laplace transform of the derivatives. So given that, where's my derivatives though? So let me see what's the derivative. So this is my derivative. Let's copy this. And I'm going to paste it here. Okay, so that goes my derivative. So I'm going to find the Laplace transform of the function given here, which is 2d square x over dt square minus 3dx over dt plus x. And I have this initial conditions given. So x naught is going to equal 2 and x prime 0 is going to equal negative of 1. So that is why. So actually, what is Laplace transform? Laplace transform is actually a method of solving differential equation. So the same for undetermined coefficient, variation of parameter, linear equation, homogeneous equation, just that we haven't started solving yet. Because when we want to solve for a differential equation by using the Laplace transform, there will be two operations involved. You have to do the Laplace transform and you have to do Laplace inverse. So that is why at the beginning of the lesson, we're just going to discuss about how to do Laplace and Laplace inverse. At the end of the chapter, then only we're going to start solving differential equation by using this method. And this is like how your equation is going to look like. So that's why you have to know how to Laplace transform the derivative. And so the thing about like the previous method that we have seen before, there are two types of solution. You can either have general solution or particular solution. But for the case of Laplace transform, because we always substitute the initial condition when we wanted to Laplace the derivative, so the outcome is always going to be a particular solution. Okay, so now let me Laplace transform this. So first step is, what I'm going to do is, step number 1, we are going to apply linearity theorem. Okay, because we need to separate this. No, let me Laplace transform this first. So let's Laplace transform this first. So I'm going to have a Laplace of 2. So instead of d square x over d square, which is quite long, I'm just simply going to replace that as x double prime. So minus 3 dx over dt is going to be replaced by x prime. And then the last one is simply going to be the Laplace of x. And I forgot to tell you about the variable at the back right here. So when you come across something like that in your equation, so when you simply have to Laplace an equation that looks, for example, Laplace of x. So this is actually not just x by itself. We know that in Laplace transform that our independent variable is going to be t. So this is actually Laplace of xt. And we have seen before, like over and over again. So the fact that when you Laplace transform, for example, a function of f of t, so it's going to become a new function. So now the f is going to be transformed to another new function we call as capital F, and previously it is dependent on the variable t, but now our new variable is going to be s. So that will be the same idea for this as well. So now when you Laplace transform x of t, so what happened to that is that it's now going to be transformed to a new variable, which is going to be capital X, which now no longer dependent on t, but it's going to be dependent on s. So just because the t is not written, it's going to be given like this, so it doesn't mean it's not there. So it's actually a variable x that is dependent on t. So let me give you another example. Let's see if you have Laplace of h. So this is simply not just h. So that is actually Laplace of h of t, which is going to be transformed to a new function, capital H, which is now dependent on s. So that is going to be what happened to the last time over here when we Laplace of x. Alright, so what we're going to do next is, after we have got this form, so we have to separate them because each of them are going to be Laplace transformed separately. And of course, as I mentioned to you over and over again during the beginning of this chapter, whenever your function is separated by minus and pluses, so they are going to be separated by using linearity theorem. So now what I'm going to do first is I'm going to apply linearity theorem. Right, so when I apply linearity theorem, so I'm going to end up with something like this. So I'm going to have 2, so I'm going to bring out the 2, it's a constant, remember, and Laplace of x double prime, so minus 3 Laplace of x prime, and the last one is going to be the Laplace of the function of x. And remember, I told you just now the fact that this is not simply just x, so this is actually a function x of t. Just don't really write it. After we have applied the linearity theorem, so step number 2 is we are going to apply the Laplace of derivative formula. So Laplace of derivative formula. Okay, so Laplace, I'm going to Laplace each of the term now. So I'm going to have a 2, just copy it down according to the formula. So I'm going to put the formula in the square bracket so that it wouldn't confuse our calculation. And according to what we have seen formula before, Laplace of x double prime is going to equal x squared capital X of s. Remember, only the first term is a capital letter, being preceded by sx of 0. Minus the last term is going to be x prime of 0. For x double prime, there will be 3 terms. Okay, then I am done with Laplace of x double prime. So this is simply done by using the formula. Then I'm going to Laplace whatever that goes next, which is going to be negative 3. So Laplace of x prime, so that will be given by s capital X of s minus, so there's no x prime, it's actually minus x of 0. So this is going to be the formula for Laplace of x prime. And of course, the last one is going to be the easiest one. So that is going to be Laplace of x. Now it's going to be Laplace of it's going to be a function of capital X, which is now dependent on s instead of dependent on t. Okay, so basically we are done. We have applied the formula. So that will be our Laplace transform. But not done in general, but we are done Laplace transforming them. Okay, step number 3. After you have applied the formula and Laplace the derivatives, all you have to do is substitute the initial conditions. Okay, substitute initial conditions. Too lazy to write in full. You know what IC is by now. Okay, when I substitute the initial condition, okay, what happened is that, where's going to be my initial condition? Let me highlight those places. So it's going to be right here. It's going to be here as well. So everywhere that is 0 or not at the back, so those are going to be initial conditions. And what is our initial conditions previously? X naught is going to equal 2. X prime 0 is going to equal -1. So this is going to be equal to -1. So this is going to equal 2 as well. So therefore, when I write my equation, so it's now going to be a 2, and I'm going to end up with s, capital X of s. So minus, remember, there's an s right here, multiply that by a 2. So it's going to be minus 2s, minus of negative, so that will be a positive of 1. And then I'm going to have a -3. So here, first term is going to be sx of s. And now my x naught is going to equal 2. And the last term is going to be capital X of s. Okay, so I have substituted all the initial conditions. If you notice now, everything is in term of xs and in term of function of s and constant. I get rid of everything with 0 at the back. Okay, step number 4 is going to be the last step, which is going to be simplify. So this is a very simple step. All you have to do is whatever term that is related to x of s, factorize them. So this is related to xs, this is related to xs, and this is as well. So I'm going to factor them out. So I'll end up with something like this. So x of s, so the first term is going to be 2s. This is for this one. This one is going to be this is s square. I copied that wrongly. So this is going to be 2s square. Okay, so when I factorize the xs, I will end up with 2s square, because this is actually s to the power of 2. And this is going to be minus 3s, and the last one is going to be plus 1. So that is how my function looks like. And now all I'm to do next is I'm going to collect all the terms that is not related to x of s, and I'm going to simplify them. And here I'm referring to this term right here. When I multiply it by 2, so I'll end up with a negative 4s. And when I multiply this, I'll get a 2. And here I get a 6. So 2 plus 6, that is going to equal a plus 8. So this is going to be the end of our Laplace transform. That is actually the outcome. Okay, so there are going to be just 4 very simple steps. First step is you Laplace transform them. You apply linearity theorem to separate them individually. And step number 2, you apply the Laplace of derivatives so that we can Laplace these derivatives right there. And the last one is simply, remember, so it's not a function by itself. It's actually a function x dependent on t, which when we Laplace transform is going to be a function capital X, which is dependent on s. And after you're done Laplace transforming, you already applied formula for the derivative. You substitute the initial conditions, so get rid of all the terms with the 0 at the back. You substitute the value, it will be given in the equation. And then after you're done with that, you're going to simplify, factorize the term with all the xs, and then collect the rest of the term and simplify them. Right, so that is all for the Laplace of derivative. It's a very simple theorem, as I tell you, and this is going to be in the appendix as well. You don't have to memorize. So here, Laplace transform of derivative, but again, you just have to know how to use them. And I would like to remind you that again. So only the first term is positive and in term of capital letter. The preceding term will be in term of negative, and they will be in smaller case. Remember, all you have to do is, you don't even have to memorize them. You just have to copy them term by term. But when you copy, please copy them correctly and make sure that you use the appropriate variable. Like if you're using df over dt, then yeah, your outcome is going to be in term of f. But if you're using dy over dt, then your outcome is going to be in terms of y. And if you're using dx over dt, and then your variable is going to be in terms of x, and so on. You just have to replace the alphabet. Right, so it's a very simple one, but a very, very, very important one. So I want you to remember this, so that by the time we start discussing on how to solve a Laplace transform, so this is still in your mind. Okay, so let's meet in the next video.